All right, our second kind of improper integrals happen when there is an infinite discontinuity someplace in between our closed interval. There's some sort of vertical asymptote. All right, and that could be on the left side, it could be on the right side, or it could be someplace in between here. So let's say that our function f is continuous on the interval. It's closed at a, it's open at b. It's open at b because there's an infinite discontinuity at b. And so here's what the improper integral would look like. It's improper, but it's in disguise. Like, you don't know because a and b are just numbers. And you have some sort of function with respect to x. We're going to turn that into a limit just like we did before, but we're going to take that b value out, replace it with something. It could be a c. You could replace it with, whatever that, some sort of variable, as long as it's not one that's already being used. And then we're going to approach that original b value from the left. In order to understand that, let's take a look at a picture here. So we have on the right-hand side, this infinite discontinuity. We have a vertical asymptote there, and we're going to approach it like if we have a vertical asymptote on the right-hand side, we have to approach that from the left, which is why this limit has c approaching b from the left-hand side, because I have to approach it from the left-hand side, okay? So once I've turned it into the limit, this one-sided limit, then I can evaluate the definite integral and then perform the limit. If the limit exists, we'll say that it converges just like on the previous ones, and we're going to say that it diverges otherwise. It's going to go shoot off to infinity, okay? Our next case is if we have an infinite discontinuity on the left-hand side at a, right? So we have a vertical asymptote at a. We're going to turn that into a limit. Again, it's in disguise. We're going to take the a out, replace it with something, and then have that something, let's say c, approach a from the right-hand side this time. So again, let's look at a graph to help us make sense of this. That if I have a vertical asymptote on the left-hand side, on my lower bound, then I have to approach that thing from the right side of that thing, which is why it's c approaching a from the right. We're going to say it converges if that limit exists, and we're going to say that it diverges otherwise. Okay, and then our third and final case is that there is an infinite discontinuity. There is a vertical asymptote someplace in between a and b, and this one is probably the least obvious one. Well, in this case, you need to break it up at that infinite discontinuity, turn it into two separate integrals, both of which are improper, and then you're going to perform these previous ones on the left side and on the right side. One like that and one like this. Okay, so here's a graph of that thing happening. We have this infinite discontinuity here at c. So I'm going to break this up. At c, perform the definite integral, or the limit, as we approach c from the left-hand side, separately as approaching it from the right-hand side. All right, so I think that this one will make a little bit more sense if I put some numbers in here so we can see how this thing is actually going to play out. All right, so let me scroll down to the one that we just did right here. Okay, so let's just say for the example that we're working with here that this is the number 1, this is the number 2, and this is the number 3. And it would not have been obvious without doing some sort of investigation that we would have had an improper integral. It would have looked originally like this. The definite integral from 1 to 3 of some sort of function with respect to x. Okay, without some sort of investigation, I wouldn't have known that it was improper. Oh, I see the graph. It does have a vertical asymptote right here at 2, so I need to break this up as two separate integrals. I'm going to break it up from 1 to 2 of f of x dx, plus the definite integral from 2 to 3 of f of x dx. Both of these things are improper. If I look at this one on the left-hand side, it's improper. It's got a upper bound, which has a vertical asymptote, and then the second one has a lower bound, which has an asymptote. Okay, and then whenever I go to set up the limits for each one of these things, one on the left-hand side would be the limit as, and what I tend to do is if it's the bottom one, I replace it with an a. If it's the top one, I replace it with, let's say, a b. So I'm going to say the limit as b goes to 2, and this is this one that the vertical asymptote is on the right-hand side of it. So I am going to approach that thing from the left, which is the negative side. So approaches 2 from the left of the definite integral from 1 to b of f of x dx. Plus, and now the second one here, also going to turn that into a limit, but this time I'm going to use an a. It's on the lower side there. 2 from the, okay, so on this side, we have the vertical asymptote is on the left-hand side, but in order to approach it, I have to approach it from the right. So this will have a little plus sign on it. Definite integral from a to 3 of f of x dx. And then we take the derivatives of each of those things, apply fundamental theorem of calculus to it, and then finally take the one-sided limit for each one of those. Okay, so now we're going to take a look at an example of one of these. I've got to evaluate definite integral from 0 to 1 of 1 over the cube root of x with respect to x. So it's not immediately obvious that this one is improper. Why is this one improper? Well, the reason why it's improper is because for the function 1 over the cube root of x, it has a vertical asymptote right here at 0. As a matter of fact, here's a graph of this happening, right? If we were to take that lower limit of integration, plug it in 0, it'd be undefined. We'd be dividing by 0. We've got a vertical asymptote here. And notice how it does seem to collapse to that y-axis pretty quickly. Might be a pretty good indication that this limit is actually going to exist. So let's give it a try. So again, I'm going to replace, I'm going to turn this thing into a limit, specifically a one-sided limit. And we need to approach that 0 from the right-hand side, so from the positive side. So this is example something, example 6. And we're trying to evaluate the definite integral from 0 to 1 over the cube root of x dx. And we're saying what makes this thing improper is that we have ourselves a vertical asymptote here. Vertical asymptote, so we need to turn this thing into a limit, which makes this thing improper. Okay. So we'll turn it into a limit. We're going to get rid of the 0. It's on the lower side. I'll just go ahead and replace it with an a. We're going to approach 0, and as we said, we need to approach that from the right-hand side of 0. So put a plus sign in there. Definite integral from a to 1, and then I'll rewrite this as x to the negative 1/3 with respect to x. All right, ignore the limit for right now. Pretend it doesn't exist, but go ahead and write it down again. And evaluate, take the antiderivative of x to the negative 1/3 power. So I'd add 1 to the exponent. That would be x to the 2/3. Divide by 2/3, which is the same thing as multiplying by 3/2. And then we're going to evaluate that from a to 1. All right, still we're not at the point where we're going to evaluate the limit. Just bring it down. And then we'll go ahead and plug in our 1 and our a. So 1 to the 2/3 power minus a to the 2/3 power. Now we're ready. Now we're ready to take the limit. Now remember that for the most part, the plus sign on the 0 are notational reasons. Like it doesn't even make sense on the left-hand side. Usually limits are supposed to approach from both sides. This one's only on the right-hand side. So as far as evaluating the limit, we still just plug in 0. It doesn't matter if it had a plus or a negative sign in there. We still just plug in 0 and see what's going to happen, because sometimes everything works out just fine. All right, so the first part of this, 1 to the 2/3 power, is still just 1. So I have 3 over 2. I got 3/2. And then on the second one here, when I take 0 from the right to the 2/3 power, it's still 0. It's gone. So that part is finished. It's been eliminated, and there's our final answer. So we're going to say that our definite integral here converges to 3/2. And again, the graphical evidence here seems to point towards the fact that it collapses to the axis quick enough that it actually does converges to 3/2. Let's take a look at another one here. Evaluate definite integral from 0 to 2, dx over x to the third. Why is this one improper? Why is it in this lesson? Again, the reason why is because we have a 0. If we had a 0 down in the denominator, we've got another vertical asymptote, and here's a graph for this one. All right, now on this one, notice how far away that graph is from the y-axis. This one doesn't look like it gets there quick enough. It gets down to the x-axis pretty quick, but that's not where we're taking the limit. We're taking the limit towards 0 here, right? Okay, so let's give this one a try. It seems that the evidence is pointing towards this one not actually working. So I'm going to actually do a little bit of coloring here because I wanna. So it's all of this region here underneath this curve. And this, I mean, it's perfect, right? It's like it came colored. All right, that's what I'm trying to find the area of, see if it's unbounded. I'm going to take the limit, and since the vertical asymptote here is at 0, we're going to approach that just like we did before from the right-hand side. So for this example, 7. I've got the definite integral from 0 to 2 dx over x cubed. We're going to take out, and well, yeah, notice, of course, that we've got an improper integral because we've got a vertical asymptote, which makes it improper. Doop. Make it a limit. Limit as a approaches 0, as we said, from the right-hand side, plus definite integral from a to 2, and then I'll rewrite this as x to the negative third power. Now we're ready to evaluate the definite integral part of this. Let's see, add 1 to the exponent would be x to the negative 2 divided by negative 2. I'm going to evaluate that from a to 2. And maybe do a little bit of rewriting here. I'll just take out this negative 1/2 here. Or, x to the negative 2. Okay, again, from a to 2. Now we're ready to evaluate it FTC style. Negative 1 over 2 squared. 2 squared is 4 times 2 is an eighth, so negative an eighth. And then minus a negative, which makes it plus. And we would have 1 over 2a squared. Okay, now we can do the limit. All right, on the first part, negative 1 over 8 is not affected. But over here on the right-hand part, this one, when I stick 0 down in the denominator, I'm dividing by 0. This should go to positive or negative infinity. Which one is it? As if it actually matters. It does matter. The number's going to be positive. Doesn't even matter whatever I'm sticking in here. This number is going to be positive. So this is going to tend towards positive infinity. So this one is infinity, which means that this area diverges. As x gets closer and closer to 0, this area is getting bigger and bigger and bigger, infinitely big. All right, it looks like this is the same exact graph, but now we're going from negative 1 to 2. From negative 1 to 2, how does that change this problem? All right, I want to do some more coloring here. So we're going from negative 1 to positive 2. So still this piece over here. And Then we also have this piece that's over here on the left-hand side. All right, so I'm going to pretend I'm going to play like I haven't already done this problem, where the right-hand side we already know diverged. But remember, there was something that we stated right up here. Diverges if any part diverges. The thing that's in the box right there, that's going to come into play, as we're going to see in just a moment. Okay, so if this problem was all by itself, I may not have known that, right? So I'm just going to go ahead and play like I'm completely devoid of that knowledge. So example, what is this? 8. And this time we're taking the definite integral from -1 to 2 dx over x to the third. Okay, so here's one where we have an asymptote that's in the middle of our the interval that we're working with. It's right here at 0. So for this particular example, we do have to break it up. Before we take limits and stuff, we have to break it up as 2 separate integrals. One that's going to approach 0 from the left-hand side, and one that's going to approach 0 from the right-hand side. So this should be equal to the definite integral from -1 to 0 dx over x cubed plus the definite integral from 0 to 2 dx over x cubed. And now I can pretty much conclude that I'm done here. And the reason why is because we've already shown that this part here diverges. By example 7, I think it was. Anyway, so since this portion of it diverges, I'm going to say the whole entire problem diverges. And that one's finished, right? I mean, it makes sense. This part was already infinitely big, so the whole thing is still infinitely big. Okay, let's look at another one. This one, highly complicated, as we're about to see. Maybe at first glance, it doesn't appear so. It should. It's got this like square root thingy in the bottom. Like, what the heck? And this will be the last one we do for this little video, which will be nice. Take yourself a little breather, bathroom break, go get yourself a snack, whatever. All right, so we're going to evaluate definite integral from 0 to infinity dx over the square root of x times x plus 1. Now this one, it's obvious that we have we've got an improper integral because the top limit is infinity. However, we also have a vertical asymptote at 0, right? If I were to take that 0 and plug it into the square root of x, which is on the bottom, I'd be dividing by 0. So this one is also doubly improper. So here's a graph of this thing. But look how close it is to the x-axis. Look how close it is to the y-axis. I wonder if it collapses fast enough to actually have a finite area. So that's what we're about to find out here. All right. So make some sort of note here that this thing improper. And then down here at the bottom, we've got ourselves a vertical asymptote. So it is also improper. And as far as the one at 0 goes, we're going to be approaching that one from the right-hand side. So that one will be a one-sided limit. The one to infinity, infinity is always going to be, you only approach that from, say, the left-hand side. Approach infinity from the right-hand side, if you please. Let's try example 9. We are taking the definite integral from 0 to infinity of, did I put the dx on top? Okay, I'm going to go ahead and do that. Over the square root of x times x plus 1. All right, and let's see. I don't have to break this up as any separate thing, but I am going to have to, actually, yes, I do need to break it up. I do need to break it up because I've got two different things happening. Where should I break it up? What makes a lot of sense? Well, I usually break things up at 0 because 0 is easy to work with, but I can't do that one. So I'm going to take the next best thing and let's break it up here at 1. That will make sense. You can break it up anywhere, but why not 1? 1 is usually pretty close to being as easy to plug stuff in as 0 is. So I've got the definite integral from 0 to 1 of this stuff. And then from 1 to infinity. Both of which are improper, right? The one that's on the left-hand side is improper because we've got a vertical asymptote here. One on the right-hand side is improper because we have this obvious unbounded upper limit of integration. Okay, so I need to turn both of these things into a limit. The one on the left-hand side, we said we're going to approach that from the right side of 0. Let's see, lower bound, so I'll make that an A. Approaches 0 from the right. Definite integral from A to 1 of whatever this thing's going to turn out to be. Having a clue. And then we've got another limit. As this one's upper limit, so I'll choose B. Goes to infinity. 1 to B of the same thing. Copy, paste. All right, so we've at least set this thing up. Now the thing is, the chore is to actually find what the heck the antiderivative of this thing is, and it is absolutely not obvious, right? You might think that, oh, what we're going to do is do some sort of u substitution, but what are you going to choose as your u? If you chose your x plus 1, your du is equal to just dx. That's unhelpful because we still have this square root of x down here in the bottom. If we chose our square root of x as being our u, then let's see, that's x to the 1/2. This would be negative 1 over 2 square root of x dx. But we already chose that one as being, like this first one as being our u, so that didn't help either. So this turns out to be another arctangent. Is arctangent in disguise for sure? Remember arctangent, I'll just go ahead and write it off to the side right over here. So the antiderivative of this is a du over u squared plus a squared. This is supposed to be 1 over a arctangent of, come on, u over a and then plus c. And that's not exactly what this looks like, but we can make it look like that, like this. So notice that for this problem, x is a positive number, right? So always some sort of positive number. So I can rewrite x as the square root of x squared, right? Okay. So if that is the case, then maybe I reimagine this integral as being, I'm just going to write the integrand here. I'm going to write it as a 1, just out of convenience, over square root of x times the square root of x squared plus 1. Okay, and so now it's looking a little bit more like what we have here, where your u is equal to, or I should say your u squared is equal to the square root of x squared, and then u is equal to the square root of x. And then it is essentially still a u substitution, so you need to take du. I think I already did that. It's negative 1 over 2 square root of x dx. And then here's where that comes into play. That is part of this. But notice that we are missing our negative 2. Oh, it's not negative. Is it negative? It's not negative. I don't know why I thought that it was negative, right? Because this is x to the 1/2. So we bring the 1/2 down. It's just positive. Yeah, it's just positive. Okay, so I just need to compensate the 2. So we'll throw a 2 in here and compensate with the 1/2 on the, nope, got that backwards. got that backwards. We need a 2 on the bottom, which means that we need a 2 on the outside, a 2 on the top. Okay, and then, well, what's our a value? So our a squared is the number that's supposed to be left behind here, which is this part here. And this means that a squared is equal to 1, so a is equal to 1. Okay, right? Painfully obvious, right? We could have just guessed all of that stuff. So now, again, whenever I'm doing the u substitution stuff with these improper integrals, it just gets too nasty to rewrite everything in terms of the u's. So I'm just going to keep everything in terms of x's and stuff, and just realize, of course, that this is an arctangent. It's basically this thing. We've just rewritten it as this here. Okay. So its antiderivative is going to be, I'll write my limits down again. The arctangent is supposed to have 1 over a on the front of it, but that a value is 1. Arctangent of our u over a, and our u we said is the square root of x. A is 1, so it's not there. It actually is there. From, what was it, a to 1? That's fine. And the beauty of this, of course, is that the second half of this is going to have the exact same antiderivative, just a different limit value. B goes to infinity, and then the arctangent of the square root of x from 1 to b. Whew! All right. Now, assuming that we got that far, now we're ready to evaluate each of these antiderivatives and take the limits of each part. So I've got the arctangent of the square root of 1 minus the arctangent of the square root of a. And now let's do the second limit here. Limit as b goes to infinity. Arctangent square root of b minus arctangent square root of 1. Square root of 1, of course, is 1. So we're taking the arctangent of 1, and that is a pi over 4. And, oh, wait a minute. Wait a minute. You know what we forgot all along the way? How come nobody spoke up? It's this 2 that's right on the outside. There should have been a 2 there. Let's fix that. 2, 2, 2, 2, and 2. Oh my gosh, I'm glad that I noticed that, since nobody else did, which means that this actually is a 2 times that. Okay. And then as a approaches 0 from the right-hand side, this is going to be the arctangent of 0. Arctangent of 0 is 0. So I'm going to subtract 2 times 0 from that. Don't add it. And we also want 2 times that 0. All right, plus, over here on the next part, the 2 times the arctangent is the square root of b. b is going to infinity. So the arctangent, whenever it goes to infinity, as we've seen about 45,000 times, this goes to a pi over 2. So we have 2 times pi over 2. Boop. And then minus, and I think that we've already done this one again. It was the same thing that we have over here. So it's a 2 times pi over 4, which conveniently cancels. Boof, boof, and forget about this thing. And then we have our final answer. The 2's, oh, wait, take out the canceling pink again. Our final answer here is pi. Of course it was pi. Why wouldn't it have been pi? Right? Doesn't it even look like it? That area right there, that pink region right there, converges to pi. All right. So that's about going to wrap up this video, where we're taking a look at some improper integrals. This one in particular had an obvious upper limit, which is infinity, but that's not always the case. It could be the upper or the lower limit is a vertical asymptote, which means you have to turn it into a one-sided limit. Or it could be that you have a vertical asymptote someplace in between, and then you got to break it up as two separate ones.